At the end of the last lesson, we talked about the polymer polyvinyl acetate and how its ester could be hydrolyzed to make polyvinyl alcohol. This is necessary because vinyl alcohol is a tautomer of ethanal or acetaldehyde, and ethanal is the more stable form. Another example of a polymer that must be synthesized in a different form is polyether-ether ketone, or PEEK. PEEK is really stable and rigid due to the conjugation over the entire length of the polymer, and will begin to form crystals if it is synthesized in its final form. That's fine, except that when crystals form, the polymer crashes out of solution and can't really polymerize anymore. You can see the regularity of the long chains of completely conjugated polymers and how they stack in layers in the figure shown. Again, these tend to fall out of solution before they can get to any sort of useful length. To avoid this, PEEK is produced with additional tert-butyl groups that disrupt the crystal interactions. Triflic acid, which is short for trifluorosulfonic acid, is able to catalyze the exchange of the tert-butyl group onto the solvent and give us the PEEK without the tert-butyl group that can finally crystallize. Polymers can be cross-linked too, as long as they have reactive functional groups. Polyvinyl alcohol, for instance, can be cross-linked with borate esters, which cause the formation of slime. Polymers can align in pretty drastically different forms, sometimes aligning very regularly, sometimes really irregularly. These regions can actually appear in the same plastic, having some ordered sections and some unordered sections. If the plastic has amorphous or unordered sections at all, it will have a temperature that is high enough to have these sections flow without actually melting, called a glass transition temperature, or a TG. The same type of plastic may have different glass transition temperatures depending on the conditions under which it was formed and the amount of amorphous character. Here we see two samples of the same type of plastic that have different degrees of crystallinity. The more crystalline sample 2 doesn't have much disordered region and needs a higher temperature to flow at all. The less crystalline sample 1 has more disorder and therefore a lower glass transition temperature. Because the glass transition temperature is sometimes different for the same polymer, we can actually change the form of the plastic by adding energy, either heat or kinetic. A plastic may start out with some amorphous and some crystalline regions. At low temperatures, the plastic can't move past itself well at all. If you bend it too much, it might break. An example of a plastic that we often encounter below the glass transition temperature is polystyrene. Past the glass transition temperature, the plastic can move past itself and is much more flexible and moldable. Plastics like HDPE and LDPE are typically encountered in this range, where we can flatten a milk jug for recycling without leaking air, or we can stretch a plastic bag to some extent without it breaking. If the temperature gets high enough, the plastic will be able to move into the most stable form, which will typically be crystals. The order that is present in crystals maximizes contact and minimizes energy, allowing a significant release of energy. Since the plastic is still in a range where it's able to flow past itself, it remains somewhat flexible. At the melting point of the liquid, the plastic becomes fully liquid, which is again disordered. We don't deal with many plastics in this range, but often plastics are molded at high temperatures. The plastic may be viscous, but it will be fluid in this form. When the plastic is cooled back down from a fluid state, the degree of crystallization will largely depend on the rate of cooling. Faster cooling will trap regions as amorphous, and slower will allow for crystallization. Kind of like how you always want to cool organic recrystallizations really slowly to get the best crystals. Where a plastic falls relative to the glass transition temperature really matters for the properties we see. A racquetball is normally above the glass transition temperature, which allows it to be flexible or moldable. If it's cooled down, as with liquid nitrogen as shown in the center image, that brings the temperature below the glass transition temperature, and what was flexible is now very brittle. It can be easily shattered. Several factors will impact what the glass transition temperature is for any given polymer. Most of the factors relate to the strength of the intermolecular forces. As with any molecule, larger molecules tend to have more London or other intermolecular forces, and so have a much higher glass transition temperature, Tg, and a much higher melting point, Tm. Similarly, polymers with strongly interacting side chains also tend to increase the Tg and the Tm. Similarly, the presence of branches on the molecule tend to reduce the contact between polymer chains and make it harder for them to interact, decreasing the Tg and the Tm. Think about the difference between a milk jug, which is HDPE, with little to no branching, and a plastic bag, which is often LDPE and has a significant branching, which makes it more flexible. The types of side chains also really matter. Polypropylene has really regular side chains, which tend to help prevent chains from rotating as freely. It requires more energy then to make them flexible, a higher Tg and a higher Tm. Polystyrene has even larger side chains, which make it more rigid, which is why it's less flexible than polypropylene. If the side chains are more flexible than polypropylene or polystyrene, we'll actually see the opposite effect. The flexible side chains, if large, can keep the main chains farther apart and prevent strong interactions, lowering the Tg and lowering the Tm. More rigid side chains allow the chains closer and improve interactions, increasing the Tm and Tg. You can see the large difference between the low Tg for a flexible N-butyl ether on the left compared to the relatively high Tg for the more rigid tert-butyl ether shown on the right. Really, anything in general that allows orderly crystals is a big increasing factor for Tg and Tm, and anything that decreases the order in the crystals will decrease Tg and Tm. The strength of interactions also really matters. Remember, covalent interactions are the strongest, like the disulfides in vulcanized rubber, then ionic, like the polyacrylate that's shown on the right. The Tg and Tm have actually gotten so high that it breaks to pieces or decomposes before it melts. Below ionic interactions are hydrogen bonds, like the conjugate acid of polyacrylate, polyacrylic acid, which is shown on the left. Now the glass transition temperature is still really high, but it becomes amorphous before burning or decomposing. Note that with really strong side chain interactions, these may improve water solubility or absorption. On the other hand, water would be preventing the polymers from reacting directly with themselves, which is also a strong interaction. So sometimes it's hard to dissolve even very polar particles. Try dissolving a hardened bit of school glue. Not that I've ever had to do this, but it's not easy. One set of examples where we can see these differences at play are the polyethylene polymers. HDPE is highly linear and much more crystalline. It is weakly interacting, having only London forces, so it has a really low glass transition temperature, but it has a fairly high melting point. Linear low-density polyethylene copolymerizes small branches, which prevent the chains from interacting quite as strongly. This interrupts the crystallinity and causes the polymer to be more flexible and the melting point to be slightly lower. Fully low-density polyethylene is much more irregularly branched. This is because when polyethylene is radically initiated, the growing end always needs to be in the primary position. This makes sense since ethene only has 2 carbons and they are both primary. If the growing end encounters any other chain, it can extract a hydrogen through bimolecular homolytic substitution and move the radical growing end into a more stable middle of a different chain. This can happen at random intervals and create a highly diverse structure that is really difficult to crystallize, maximizing the plastic behavior and decreasing the melting point. So if LDPE naturally branches, how do we get the unbranched version? Many alkene-based plastics are produced with much more robust control using Lewis acid catalysts, such as the Ziegler-Natta catalyst shown. The Ziegler-Natta catalyst initially acts as a receptor for the pi electrons of 1-alkenes like ethene and propene. Because the Ziegler-Natta catalyst is an early transition metal, it also has some extra electron density weakly held in a different d orbital that has the correct symmetry for pi overlap with another pi antibonding orbital. This contribution to the pi antibonding orbital allows the bond order to decrease and more electron density can move into a single carbon as a sigma bond. This in turn weakens the metal bond to the other carbon, which can jump to the vacant position of the double bond. The rearrangement regenerates the opening on the catalyst, which can continue to add alkenes and rearrange them into the chain, but never generates a mobile free radical. Other Ziegler-Natta catalysts can ensure particular control over the direction of any side chains, which is actually really powerful for tuning the properties of plastics. Another way we see the side chains affecting properties is with polystyrene, which is a large, regularly repeating, and rigid side chain. This increases the Tg and Tm to the point where it functions more like a traditional solid, since it's well below the glass transition temperature at room temperature. The melting temperature is high enough that the polystyrene will depolymerize or burn long before it would actually melt. Many plastic containers are produced by injection molding. Because polyethylene terephthalate is inserted into the mold above its glass transition temperature on a heated stretch rod, it's moldable. The stretch rod pushes the plastic down into the mold, which pulls crystalline regions in greater alignment and therefore increases the rigidity of the plastic. It's blown to fit the form, but when it's cooled, it's generally unlikely to significantly deform under pressure. This is really helpful if you're going to fill the bottle with fizzy lifting drinks. Polymers are formed through reactions, and they can also be broke through reactions. When a large molecule is broken down, we say it's degraded. In the case of polymers breaking down into monomers, we call this depolymerization. There are many forms of these reactions. Some of what we talk about here has really direct applications to how we talk about proteins and polysaccharides, which are both biopolymers. When we talk about proteins, we will often talk about primary structure, which is essentially the structure of the main chain of the amino acid polyamide. Similarly, there is cross-linking possible. This cross-linking is often within the protein rather than between protein strands, so it increases the rigidity of the protein structure rather than increasing the bulk rigidity of a material such as in plastic or vulcanized rubber. We also have regions within a protein of higher order, alpha helices and beta pleated sheets. These highly ordered regions are stabilized by strong, regular interactions within the main chain and amount to a high degree of crystallinity, which is going to increase the melting point of a protein. Again, for a protein, this is a little bit different than from a plastic. In a plastic, the melting point would allow for an entire plastic to move freely. In a protein, the protein would denature or unfold at the melting point. We often display protein structures with ribbon displays, where alpha helices and beta sheets are coated with a particular appearance, to make these areas of higher order much more apparent in the 3D structure. Weaker interactions often stabilize the 3D form of the structure. Most of the inside of the protein is actually nonpolar. Although it seems like it'd be easier to stabilize the protein structure with stronger polar interactions, certainly that's the case in polymers, most proteins are individual molecules that are suspended in water. Any polar interaction between the protein side chains can just as easily be replaced by the water, where the nonpolar interactions are much harder to replace when you're in water as a solvent. Some proteins actually assemble multiple peptide polymers together, which then need to be stabilized relative to each other. Order at this interface between peptides allows the peptides to interact strongly and selectively and not fall apart, essentially akin to increasing the melting point for that interaction. We call this assemblage of peptides quaternary structure in a protein complex. Similarly, polysaccharides are polymers and are subject to some of the same considerations also. Two of the most common polysaccharides, amylose, aka starch, and cellulose, are both polysaccharides of glucose that are linked at the same carbon but in opposite directions. The orientation of the glycoside bond that connects glucoses in amylose causes amylose to take on a somewhat cyclic structure that can bond readily with water and be highly soluble. Because cellulose is inverted, the glucose-glucose connection allows hydrogen bonding between the glucoses and causes that chain to be much more rigid, and it's able to hydrogen bond with water far less. This allows cellulose to have a much higher Tg and a much higher Tm and a much more crystalline structure that is now water insoluble. This is the very last slide of the last semester of OChem, and it's the point where you finally know all things. Congratulations. Go forth and do great things with your overloaded brain. Don't be strangers, at least don't be strangers once COVID-19's gone.